Welcome everyone to the MidNite Power training on generators. We're going to talk a bit about generators in general for off-grid systems, types of generators, general philosophy of using generators for backup on off-grid solar power, and then go into some of the details of using a generator with the MidNite all-in-one inverter, using it on the gen input terminals or the AC in terminals, and go through the programming in the app of how you set up the generator. And then we'll talk a little bit about what some of the common causes of what do you do if your generator won't charge the batteries. It's running, but it won't charge. Starting with generator types, we've got lots of different ways we can break them out into different types. Portable versus permanent pad-mounted generators is a big one. Generally, we don't recommend using portable generators with our inverter, and this is for a couple reasons. One is just the size of these generators. Really, you want a 12 to 15 kilowatt generator minimum to work well with this inverter, and we'll go over why that is when we talk about sizing generators. But there's not a lot of the portable ones that are that large. Portable ones are often not designed to be very durable, so they aren't a good long-term solution for an off-grid PV system for backup. And often the power quality output from these small portable generators is not that clean, which can cause problems either with passing through that power to your loads while it's charging or just actually charging the batteries. Some of them are better, so that's not always a problem with portables, but it's a common issue we see. Another issue with portables is that a lot of them have built-in ground fault protection, and the inverter needs a generator that does not have neutral and ground bonded at the generator. If they're bonded at the generator, that can cause problems. So you'll need one that you can make sure they're not bonded there and do a hardwired connection versus a 4-wire connection with a ground and a neutral that are bonded together on a GFI. Also going to mention that we need 120 240 split phase 3-wire power to work with the inverter. Just plain 120 volt generators will not work, and 240 volt single phase European style generators won't work. It needs to be 120 240 split phase output. When looking at generators, we also start looking at standby versus prime power generators. Standby is generally what we're using until we start getting into the 30-40 kilowatts or larger. There are some smaller prime power generators. Standby is generally intended for backup power for the grid, versus prime power is designed to run 24 hours a day for a complete off-grid generator powered situation. Standby tend to be lighter built, lower runtime before they need rebuilding, and just really not as heavy duty. And this has some limitations when we're using them for battery charging, which is a lot heavier load than typical backup power for a house is. Looking at air-cooled versus liquid-cooled, generally most of our standby ones are going to be air-cooled nowadays, and often those are 1,500 to maybe 2,500 hour expected runtime before they're worn out. Liquid-cooled ones usually run at 1,800 RPMs instead of 3,600 and have much longer design lifespans, often 10,000 hours between rebuilds or replacements. In the sub 20 kilowatt size, it's a lot harder to find the liquid-cooled long life ones, but there are still some options there. What size generator? The MidNite inverter can pull 10 kilowatts for battery charging, and that's in addition to the pass-through for loads. So usually we recommend a 12 to 15 kilowatt generator minimum, but it can depend on your situation. You can reduce the battery charging rate to allow using a smaller, say a 6 to 7 kilowatt portable generator. It's just going to charge the batteries at a lot slower rate, and you really want to watch out for overloading those smaller generators and really causing even shorter lifespan on them. One mention is inverter generators. These actually have nothing to do with inverters in PV systems. They're just a different design internally, which actually does have a small inverter in the generator. They can have better power quality for small generators versus the non-inverter type small generators. I don't know that I've actually seen an inverter type generator larger than about 7 kilowatts maximum, maybe. So while inverter generators are perfectly compatible with our inverter in theory, just the sizes that they typically come in mean that you probably won't be using one of those on a system with our inverter. When we're looking at generator sizing, we need to include a couple D-rates in there versus the nameplate on the generator. Altitude's a big one if you're operating at higher altitudes. Where I worked a lot in Colorado, we were usually using a 30% D-rate for altitude, 9,000 feet altitude and above. And that's a significant D-rate. Take a 15 kilowatt generator and suddenly it's really more like a 10 kilowatt actual output. We also want a D-rate for continuous use, because when we're charging batteries, we're drawing that full power for long periods of time. And most of them, even though they have a continuous rating, really aren't thinking about that it's going to be that full max load for a long period unless they're a prime power generator. So when we're talking about standby generators, and especially air-cooled standby generators, most of those, we don't want to run them more than 4 hours at that maximum power, even accounting for these D-rates when we're charging batteries. And that's one reason why a lot of generators will have a different warranty period if used off-grid. So typically we might see a 2,000 hour warranty if used on-grid as just backup power, but only a 1,000 hour warranty if used off-grid, because they know that's a lot heavier kind of service on that generator, and it's possibly not going to last as well. And one thing we can do to mitigate that is really derate them, and we might only be pulling, say, 10 kilowatts out of a 20 kilowatt standby generator when we take all these derates into account to really keep it happy long term. If you're just using it a few hours a year for backup power, it's not as critical. But if it's a situation where deep dark wintertime, you're running it every afternoon for 2 or 3 hours, that's really where you want to think about, how can I make this generator last longer? Fuel types, we've got gasoline, propane, natural gas, and diesel. Typically, I don't use a lot of gasoline ones just because of the size. And like I said, once we're looking at the 12 to 15 kilowatt size, we're usually looking at a permanent pad mounted one, and those are generally propane, natural gas, or diesel. Most off-grid situations don't have natural gas available. If they do, great, but most of them don't. So propane is really the most common fuel that we use. Most off-grid houses where I've worked already have propane on site, and propane generators tend to start a lot better at cold temperatures below zero than diesel ones. In warmer climates, diesel generators for backup can be a good option, especially once we get into the larger sizes, 30, 40 kilowatts and above. most of those are the water-cooled, more durable, long-life ones. And when you don't have cold weather starting problems, that can work out pretty well. So any of these fuel types can be used, but it's just the nature of off-grid systems kind of tends to push us more towards propane in colder climates and diesel for warmer climates, just because that's the type of generators that are typically available in the size ranges that we're looking for. When we're designing an off-grid system, one of the questions is, how much generator runtime is best? How much should I get from solar and how much should I get from generators? And this will vary depending on your particular climate, but the general thought is we want to use the least expensive type of energy generation we can. So the question becomes, what's the least expensive type? PV has a higher capital cost, but a long life and zero fuel cost. So once we've installed our PV array, it's very cheap. However, if we have cloudy weather, we've got to install a lot more PV than we do in sunny weather, so it's more expensive then than in full sun. And at nighttime, obviously, we can't operate straight from our PV array. We've got to add solar panels. So that's where we're going to add batteries. Then we have more capital cost, more cost, lifetime cost. So during the daytime on sunny days, that's when we've got really cheap electricity from the PV. We'll do some example numbers here in a minute. But on cloudy days and at nighttime, we start adding batteries, more batteries for longer periods, and the cost starts going up. At some point, it makes more sense to switch to running a generator. The generator has a lower capital cost, but it has a higher fuel and maintenance cost, and if we start running it a lot, we're going to be ending up paying more than if we just had more batteries in PV. And where those two lines cross, where your generator costs going up with more runtime and your PV costs going up as you get more into cloudy periods, that's kind of the question. Just going through some quick examples. These are not super accurate, but just kind of designed to give you an idea of the general magnitude of what the numbers we're looking at are. So we're going to look at a 10 kilowatt PV array, look at the capital cost and how long it lasts. And if we take all the energy that PV array could generate over its lifespan, it's 2.7 cents per kilowatt hour. That's really cheap. But when we're looking at off-grid, we may be oversizing that array to really produce enough to use on cloudy days. Then the effective cost per kilowatt hour on those cloudy days is quite a bit more. If we've got, say, a 4 times oversized PV array, now we're up to 11 cents per kilowatt hour. Still not bad compared to other sources, but it's quite a bit more than we were looking at before. And like we said before, at nighttime and as we go into darker snowy periods, doesn't matter how much PV we've got to use batteries. So what's the cost of those batteries? Looking at lithium battery, 40 kilowatt hours of storage, and amortizing that cost over the 20-year lifespan of the batteries, we're costing 4.1 cents per kilowatt hour for battery storage. So each kilowatt hour that we put into the battery and draw back out that night adds an extra 4.1 cents. What if we need to store it for longer? Now we've got to have a much larger battery bank, and it's just to get us to that last day of storage. So effectively, the cost during that last day is a lot more. In this case, after 5 days, we're up to 21 cents, and that's our storage cost to reach that 5 days in. If we've got 2 weeks, now we're all the way up into the 60 cents range. So you can see that trying to store energy for long periods starts getting very expensive effectively to get to the end of that long period. That's where it can make sense to, instead of just adding more batteries, switch to running the generator. How about the cost of the generator? Here we're looking at, this is a kind of medium range standby air-cooled backup generator. Capital cost, and assuming a 2,000 hour expected lifespan, about 20 cents per kilowatt hour for the capital cost amortized over the life of the generator. That's already pretty high there. Fuel cost, assuming propane here, we're another 35 cents per kilowatt hour for fuel costs. So our total cost to run that generator for a kilowatt hour is 55 cents per kilowatt hour. That's pretty high. That's a lot higher than typical grid power is, and a lot higher than a lot of our numbers we are looking at for solar. So results is that on a sunny day, our PV is a lot cheaper. Even on a cloudy day, the PV is cheaper. Overnight, our PV is cheaper at 6.8 cents per kilowatt hour. After 5 days of battery storage, we're starting to get up there. It's still only half the total amortized cost compared to the generator. However, look at how the capital costs are going up for the PV and battery system. It's not just amortized costs over those 20 years. Sometimes it's also what capital costs can we deal with. Because the PV and the batteries, we're paying everything up front, whereas the generator, a large portion of that is going to be in fuel cost, maintenance costs, which we didn't even include in that 55 cents per kilowatt hour, and replacement costs of that generator. It's probably not going to last that entire 20-year lifespan that everything else is, so you're going to be replacing it a couple times along there, whereas the PV, all that capital cost is up front. So there's a trade-off. Do we want the cheapest power over the full amortized lifespan, or a trade-off between capital costs versus operating costs? So somewhere in there we're going to say, okay, the generator might be more expensive in the really long run, but we just can't afford $178,000 of batteries in this example to give us 2 weeks of full battery storage. What we generally come up with is that we want to use PV anytime it's sunny and size the battery to last at least 1 or 2 dark days. And we also want to oversize that PV array somewhat to provide the full needs on somewhat cloudy days, probably 2 to 3 times the sunny day size. This can vary a lot depending on your particular climate. And then after that, we use the generator. If we're sizing our battery bank for a week, that can get really expensive. And we also have the problem that we can't recharge a battery bank that large very quickly unless we've also really oversized the PV array, which is even more cost. And we end up with a situation where we're constantly having a battery bank that's nowhere near full, even though it's very large, and that's not all that helpful. If we're running the generator on the very first cloudy day we have, or if the battery doesn't even last overnight and we've got to start it early in the morning, each morning before the sun comes back up, that's where we know we really have insufficient battery storage and insufficient PV array, that we're running the generator a lot more than we need to, and that's going to lead to situation I often see in off-grid houses where there's just a line of old worn-out generators sitting out behind the power shed that every 5 years it's worn out and it's on to the next generator. I've seen ones actually where they've worn out nice prime power generators every 10 years because every morning the generator was running for 3 hours before the sun came back up. So that's a sign that your battery bank is really not large enough and you need a larger battery bank and or more solar power. So that's kind of an average. It can vary on your particular situation, but generally, if you're trying to go for days and days of really bad, cloudy, dark weather, that's where it makes sense to just switch to a generator for backup. And typically you'll find it's 10% of the total power, maybe somewhere around there. But don't be starting your generator on the first cloudy day or just because you can't make it to the next morning. Another question that this brings up is, how often do we need to get the batteries full? With lead acid batteries, we needed to get them full regularly, weekly to every 2 weeks, just for the long-term health of the batteries, to keep them from sulfating. Lithium batteries, they don't care for battery health about getting to 100% regularly, but you do need to get there regularly, once a week or every 2 weeks, just to keep the battery management system, which is reporting your state of charge, keep that calibrated well. It can get out of calibration, and say it gets 1% out of calibration each day that it's cycling and doesn't get up to 100%. That doesn't seem like a lot, but over 2 weeks, that's 14 days. That could be 14% different. And if you think your batteries are at 20% and they're really at 6%, that could be a major problem. So that's why we want to get them up there regularly to keep that battery management system calibrated and have an accurate state of charge that the battery's reporting. For lead acid batteries, getting them to this 100% regularly with the generator was really pretty obnoxious, because after about 80% to maybe 90%, depending on the temperature of the battery and the particular type, they would hit full voltage and you'd have to taper charge for another several hours to get them all the way to 100%. And that led to much longer generator run times and less efficient use of the generator as we really started tapering down and not using the full capacity. What this often led to is behavior with generator charging where we'd wait till the batteries were dead, charge them up halfway or most of the way until the lights stayed on, but then not all the way. And this led to very poor battery health and sulfated lead acid batteries, because they never got completely full, just because it was so obnoxious to get them completely full with the generator. Lithium batteries, they can be charged at high rates to 95% or even higher before you have to start tapering. So it's a lot easier to get them very close to full and then just let the solar top them off. If you really don't have any solar input, then you may need to really get them to 100%, say once a week with the generator. But if you've got some solar input, it's a lot more amenable with lithium batteries to get them pretty close and let solar finish it up, and not really be worried about damaging your batteries like we had the issues with lead acid batteries, where not getting them full really led to sulfation and poor lifespan. When should you start the generator? The common method of doing it was often when the batteries shut off. That's a really bad way to do it. That's like waiting to fill up your car with gas till you run out of fuel on the side of the highway. Oh, I guess I should fuel up now. But now it's really obnoxious. With lead acid batteries, that was damaging the batteries. With lithium batteries, by the time the batteries shut off, they'll actually shut off before they damage themselves, but often that requires a manual restart of the batteries when they shut off, so it's really not the best operational procedure. Lithium batteries, we can go pretty low, but when should we start the generator? 25%? 10%? A lot of people really want to get the absolute maximum out of the batteries and try to take them as low as possible. But the problem with this is that what if that state of charge is not 100% accurate? Like I said, the state of charge can drift from reality depending on how long it's been since it's been at 100%. So if we're going to wait till 5 or 10% to start the generator, is that really 5 or 10%? Or do we have a 10% error and it's 0% before we started it, and now we have a black start situation? I would generally shoot for 20 to 25% as the minimum where I want to start the generator, just to not get too close to that bottom end. The situation where I might go lower is if I know that the sun's coming out in a couple hours. It's early in the morning and batteries are at 25%, but I know that in a couple hours I'll have plenty of sun to recharge them and I won't have to run the generator. Going a little lower might be okay. But if I'm in the middle of 3 weeks of dark fog and I'm at 25%, what does it gain me to go to 10% before starting the generator? It puts off starting the generator for a couple hours, but I know I'm going to have to run it anyway, so I might as well just start it and keep clear of those low state of charge issues with possibly shutting off and having to do a black restart. How high should we take the batteries? Should we take them all the way to 100%, near 100%, or just kind of do a boost it from 25% to 50% and then shut it back off? It depends again on kind of what the situation is. If we're expecting better weather to come back pretty soon, maybe just boosting them up to 50% and see how the next day's sun is might be good. If we know that we're in this for the long haul and we don't have much solar input for days, we might as well go all the way back up to 100% and recalibrate that BMS and call it good, because the sun's not going to get there. If we know that we've got a little bit of sun, we've got maybe cloudy conditions, but our array is still producing 10 or 20% of rated capacity, we might go near 100% and then let the solar take it all the way up to recalibrate the BMS. So it really depends on what the situation is, how high you want to go. But what we see a lot is long periods of dark, cloudy weather, and everyone's just kind of bouncing between 25% and 50%, long enough to keep it going for the next night, and then they got to run it again. That's really not the best way to do it. Better to just let it run for longer and charge it all the way up. However, considering that we don't want to run for too long on our air-cooled generators at one time and risk overheating the generator there. So some competing things there. One thing that our inverter does not have, which was common on a lot of AGS automatic generator start systems, was quiet hours that you could set where the generator wouldn't start. And I'm going to explain why I don't think those are as relevant anymore with typical lithium battery designs. When we had large lead-acid battery storage, we would usually set the generator to start around 50%, and that battery bank was often sized for several days of storage. And also, the older systems tended to have fewer loads at nighttime. Usually maybe the refrigerator, that even might be on DC power, but not a lot of constant overnight loads. Therefore, another couple hours of draw, if we hit that 50% state of charge where it would normally start the generator, it might draw it down a bit more, but still above kind of our minimum allowable draw for a lead-acid battery. So it's okay if we wait a couple hours and then start it in the morning. With the current system design with lithium batteries and a lot heavier system loads at night, A lot of heating systems that run all night, and servers and routers and internet and everything running all night. We have higher nighttime loads a lot, and we often are only sizing that battery bank for 1 or 2 or maybe 3 days of storage just because of the cost of lithium batteries. And we're waiting a lot more before we trigger that generator start. Say we've got it set at 25%, and we've got a smaller battery bank relative to our load. So another couple hours of draw could put us down where we risk our battery shut down and having to manually restart the batteries. So because we're using batteries where we can use a lot more before we have to start the generator, that gives us less reserve to go a couple more hours before starting it. So what I've seen with people using quiet hour programming on lithium batteries is they end up having shutdowns before morning, whereas with a lead acid system, you weren't playing it nearly as close to your absolute limit, so it made more sense. With these type systems, it's better to run the generator in the evening to top up the batteries. If you see in your state of charge, know that you're not going to make it till morning without a generator run. Just top it up in the evening rather than having it shut down overnight. Moving on to exactly how it works with our inverter. We have a dedicated generator input, that's smart load 1, and it can be set to be the generator input. To change it, the inverter has to be in standby, and then you'll want to do a dark start of the inverter, turning it off and turning the battery breaker on the inverter off. Wait a minute, then restart it, and wait 5 minutes, then program the settings. And that will let it get into its brain that what used to be an output is now an input, and allow all the settings to take effect properly. If you just do it quickly and don't do the dark start, we've had issues where it still shows up as a smart load instead of changing to generator input sometimes. Our maximum input amperage is 60 amps, 14.4 kilowatts, and this can be adjusted lower for smaller generators, so remember to derate your generator appropriately. And the max battery charging power can also be set separately, and that's 10 kilowatts. So the 14 kilowatts is kind of your total battery charging plus pass through 2 loads while the generator is running. The 10 kilowatts is the maximum amount to the battery charging, and it will back off on that to keep the total input less than the maximum that you set. You set the maximum runtime, and this is the maximum it can run per day, not per start. If you've got a situation where the generator is starting multiple times per day, usually that's a sign that you've got a way too small of a battery bank, unless it's like a special situation that only occurs rarely. But if regularly you're running multiple times per day, you really should have a larger battery bank there. You set the standby time, which is the cool down time of the generator after it stops charging before it shuts off. This only applies to the auto mode. In manual mode, you're manually turning the generator on and off. And you can set the start and stop state of charge. If you're using voltage as your controls, say an open loop lithium battery or a lead acid battery instead of our batteries, then you're going to have voltage controls instead of state of charge controls. With the MidNite batteries, like we said, we don't have to get them up to 100% regularly, but you want to think about keeping the BMS in calibration. So think about that when you're setting your stop state of charge, what you want to do with that. Start state of charge, like we discussed, I usually recommend around 25%. You can go lower, but you're depending on the situation, it may not really be worth it. Dry force is your AGS output, and this is terminals 1 and 2 of the dry force terminal block. These are made for 20 gauge to 26 gauge signal wire with ferrules on it. You can use small gauge solid wire like thermostat wire, but they don't work as well in these terminals as ferrules on stranded wire. And stranded wire without ferrules is very difficult to use. So it's about $30 for a tool that crimps ferrules on signal wire. So I'd highly recommend getting one of those for doing all the signal wires. If you're doing stacked inverters, you'll need those for the stacking cables as well. These terminals are rated for 30 volts and 1 amp maximum. So most generators are just doing a sense whether those terminals are connected or not, but some generators will output voltage through those contacts, so you need to think about what voltage is that. If it's sending a 12 volt signal through there, that's probably fine. Every once in a while we'll find one that's sending a 20 or a random voltage through there, or even 120 volts AC through that contact. So just because you've got a 2-wire start generator, think about what exactly is going on and whether you might need an intermediate relay in between there if it's putting voltage back on those contacts that's more than what they're rated for. You'll want to set your dry force contact to auto if you want to auto start and stop the generator at the programmed state of charge. If you're using a manually started generator that's not under the control of the inverter, you're just starting it yourself, or you're using some other type of control to control it, then you need to set the dry force to on. This isn't actually controlling the generator, but it's telling the inverter, look for AC power coming in on the generator input. So that's something that throws a lot of people off, is that when you're using a manually started generator, you have to set the dry force to on to let the inverter know to look for a generator. Another option for wiring the generator is connecting it to the AC in. So you're off grid, there's no grid coming in there. You can use a generator on that port. You might have 2 different generators you wish to use, or you might be using a large generator and want the full 100 amp feed through to the loads instead of being limited to 60 amp from the generator input terminals. So the AC in terminals are default to very, very tight frequency and voltage parameters, and that's because that's what's required to connect to the grid. A lot of generators don't meet that tight of control requirements. Most of them smaller than 100 kilowatts or even 500 or 600 kilowatts can't meet those requirements. So you're going to have to go in and adjust all the grid voltage and frequency settings, which are now basically adjusting it to let it connect to a generator on those terminals instead of the grid. So those can be opened up a bit to allow it to stay connected to a generator on those terminals. One thing to be aware of is if a generator connected to the AC in terminals drops below 56 Hertz, some of these inverters, mostly some of the really early firmware, so if you've got up-to-date firmware, this shouldn't be an issue, but some of the really early firmware, those inverters would reset themselves to 50 Hertz instead of 60 Hertz and have to be reprogrammed by the factory. Can be done remotely, but it's kind of a hassle if your inverter all of a sudden switches to 50 Hertz. So newer firmwares, this shouldn't be a problem, but also make sure your generator, if you're connecting a big generator, has good frequency control on it. Most of the bigger ones do, but some small ones vary all over the place, especially some of the cheaper ones. I've seen them drop into even the high 40s for frequency under heavy loads when you can hear that engine bog down. That's also a sign you're overloading the generator if it does that. The inverter needs to obviously set for 0 export and 0 feed-in power to the grid, which is now a generator, because you never want to export power into that generator. And the AGS function cannot be used to start a generator connected to the AC in terminals. And that's because the AGS, when it tries to start a generator, it expects that generator voltage to show up on the input terminals. If there's voltage on the AC in terminals, it says, oh, the grid came back, I don't need to run the generator, and it turns off the signal, and then your generator will stop. So it just gets all confused. We are working on some newer firmware where you can select the AGS function to work with either of the inputs. So coming soon, that will be changed. But for now, the AGS function only works on a generator connected to the generator terminals. There is a way that you can get some control over a generator connected to the AC in terminals for automatic starting and stopping. And this is to use the smart load C, that's your 30 amp smart load, to go to the coil of a signal relay and then connect an output terminal of that relay to the 2-wire start terminals of the generator. So by controlling when that smart load C turns on and off, you essentially start and stop that generator. You won't have the advanced functions, but it can do that. And remember that in this case, you're not going to have any delay or things like that. So make sure you've got your voltages or state of charge settings far enough apart that you don't have short cycling of your generator. Talking a bit about black starting batteries. This is when the battery BMS has shut down due to the empty batteries. This is not when the inverter has shut down due to hitting that low state of charge setting on the inverter. That will shut off the AC output of the inverter, but its brain will still be on. It'll show stuff on its screen. If the battery gets low enough, it'll actually shut down its output and the inverter will go completely black. So we need essentially, in that case, a way of recharging that battery, but our inverter won't turn on because it can't get power from the battery to turn its brain on. So there are two sources that'll turn the inverter on other than the battery that can turn it on and start charging that battery to get it restarted. This is either the DC PV input to the inverter. So if the sun comes out on our PV array, it'll become live from that source, or AC power to the AC in terminals of the inverter. We can't fire up the inverter's brain and get it going from AC coupled PV or from AC input on the generator in smart load. And that's because those are both controlled with relays that don't turn on until the inverter's up and running. So, what do you do about black starting your batteries? Using your DC PV input is one way, but if you manage to get in a situation where you shut down, probably it's because you didn't have much solar resource at the time. Best is to have your settings such that you shut the inverter down before the battery shut down and don't end up in this situation, but it can still happen. One way is have a separate lithium battery charger that runs off of AC that can restart the batteries. It's about $100 to $150 for a 15 or 20 amp 48 volt lithium battery charger that you could wire in such that if you need to, you can run generator power into that and bring those batteries up enough to turn the inverter back on, get the battery BMS turned back on, then turn the inverter back on, and then start charging through the normal generator port. Or we can use the generator on the AC in terminals to black start the batteries. That's if we've already got those all programmed with proper parameters so it will accept generator power through those terminals. So kind of two options there to black start the batteries from an AC source, a generator, when we don't have PV and we've accidentally gotten to the point where our battery BMS has shut down completely. If we've got our generator running and it won't charge the batteries, here's some common things to look at for why is this the situation. Look at, is the voltage and frequency of our generator within spec? We've got a pretty wide window we can operate from, but sometimes, especially some of the really cheap small generators, they may be bouncing outside of this window, even if just for a second or two, and it may not be connecting. It watches this power for sometimes a minute to 5 minutes before connecting to make sure it's stable enough to use. So if you've got a generator, I've also seen this with a generator with the voltage regulator going bad, that it just wouldn't connect because that generator was sending out spikes of voltage that were out of spec. Another thing to look at is, what are the settings for our AGS? If the battery is above the stop state of charge for the AGS, it's going to ignore the voltage on the generator input terminals. This is a common problem if we have a manually started generator and it still will only charge in between the stop and start settings on the AGS, even though you've manually started the generator. So often if we have a manually started generator, we just want to set the start and stop SOC really high, like 90 and 95%, or even 90% and 100%, to make sure anytime we manually start that generator, we're going to be below that stop setting of the AGS and it's going to start charging. And checking if we manually started it, did we set the dry contact to on to let the inverter know to look for a generator on that AC or that generator input? Is there voltage on the AC in terminals of the inverter? If there is, it'll default to using that instead of the generator input. And also give it time to recognize the generator input voltage and to qualify that input voltage and make sure it's all within the proper ranges before it begins to charge. And remember that it can't be used to dark start a battery through the generator input terminals. The inverter has to already be on, its brain on, and be able to watch that generator voltage and then close that relay to start using it. Going through what you'll actually see in the app when setting up this programming. So this is when you go to Power Control, Smart Load, set it to Generator. Remember to dark start the inverter by shutting it down completely, shutting off the battery breaker for a minute, and then turning the battery breaker back on. And then you can go through these programming steps. You'll set the maximum power input from the generator, maximum charging power to batteries from the generator, and your start and stop state of charge. Like we discussed, when you're looking at your start and stop state of charge, if you're auto starting, this is when you want it to start and when you want it to turn back off. If you're manually starting it, you want to set these really high so that it'll always be below them when you manually start the generator, and it'll accept that generator input. And then you want to set your dry force control to on if you're using a manually started generator, and auto for an auto start. Set your maximum standby and max runtime. Standby is your cooldown time, and max runtime is per day, remember. And you can also set an exercise cycle to exercise the generator weekly or monthly. In the summertime, it's good to let it run occasionally so it doesn't sit all summer, and then in the fall, when it starts getting cloudy, all of a sudden you realize the starter battery on it went dead or something else happened and it won't start. Exercising it every once in a while. A lot of generators have this built into their own controls. They will exercise themselves rather than having the inverter do it. Some don't. And that wraps this up. If you've got any questions, email me, zeke@midnitepower.com or support@midnitepower.com, and we'll answer them. Thanks for watching.